Srimati R. Padmavati, Head of Department ECE, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Electronics Honors Analog Electronics. So now we are going to learn about the small signal analysis of JFET, in which the common source configuration in which the voltage gain parameter we are going to calculate, and next is common drain and common gate configuration, for which we are going to calculate all the impedances and the voltage gain. So this is what we have discussed in the earlier session. So the AC equivalent circuit for the common source configuration of it has been given here, with the resistance, internal resistance small rd. So with this internal resistance we are going to calculate the voltage gain. And what is voltage gain? It is the ratio of the output voltage to the input voltage. So the Kirchhoff's voltage law at the input side will give you Vi, this is the input side of the circuit, Vi minus Vgs minus Vrs equal to 0. For this input side we are applying Kirchhoff's voltage law. So Vi minus Vgs minus Vrs is equal to 0, and from which Vgs is given as Vi minus, what is Vrs? It is Id into Rs, that is the drain current into the resistance Rs. And the voltage across the internal resistance Rd using Kirchhoff's voltage law is given as V naught minus Vgs. When you look at the circuit, the voltage across this resistance, that is what we are given here. It is given here, the voltage across the resistance Rd is given as this voltage minus this voltage. It is connected between the node A and the source terminal S, and the voltage difference between these two nodes is the voltage across the resistance Rd. So this voltage is VO, that is V naught, minus this voltage is Vrs. So V naught minus Vrs, and what is this current I dash? It is the current flowing through the resistance, small resistance Rd, that is the internal resistance Rd, this current, the current flowing through this resistance Rd. It is given as this voltage, the voltage at this node A minus the voltage at this node, that is the terminal S, divided by the resistance. So here the current direction is away from A. So this voltage minus this voltage. If it is reversed, then you have to take this voltage minus this voltage. So you have to look at the arrow mark. This arrow mark shows you the direction of the current, and so you have to calculate from the point where it is drawn through the resistance. So Va minus Vs is the voltage divided by the resistance will give you the current I dash. So here Va is the output voltage Vo minus Vrs, this is the source terminal voltage, minus Vo minus Vrs by the resistance Rd is the current flowing through the resistance Rd. The application of the Kirchhoff's current law will give you Id equal to GmVgs plus this is the current I dash. The current I dash is replaced with this term. So you look at the Kirchhoff's current law now, it is Id, it is flowing towards these two nodes are one and the same, it is highlighted in blue. So it is flowing towards the node Id, and these two currents are away from the node, and we have got the relationship between Id and I naught, and so you need not to worry about this I naught. We know it is the reverse of the current, Id is the reverse of this current, or I naught is the reverse of Id. So you can look at you can take the equation as ID is the only current towards the node equal to, these are the currents flowing away from the node. So, GMVGS plus I dash is replaced with this term, and from this if you rearrange every all these things, that is if you replace what is V out, that is minus ID RD, minus what is VRS, it is ID RS divided by RD, and rearrange this term, this equation, we will get ID equal to GMVI by this total term. We know what is V out or VO, that is minus ID RD equal to, we just now we take the, we have calculated what is the drain current and replace the drain current here and get the equation from this equation, get the voltage gain V out by VO by VI. So, here we have VI. So, take this to the denominator on the left side, you will have an equation, and if you assume the resistance, the internal resistance RD is greater than 10 times of these two resistances RD plus RS, then you can neglect this part, and so you will get GMRD by 1 plus GMRS. So, here the negative sign shows you the relationship, the phase shift between the input and output is 180 degree. So, this is the voltage gain of the FET in common source configuration. We know that in common source configuration we will have amplified signal with the inverted one. So, you this sign shows you the inversion between the input and output signals. And next is the FET in common drain configuration. It is a common drain configuration in which the input is given to the gate terminal and output is across the source terminal, taken across the source terminal, and to the drain terminal you have given the supply voltage, and these two resistances are used for biasing the FET, and the capacitances is going to block the DC voltage from the preceding and succeeding stages, or which is going to block the DC voltages, and which is not going to affect the bias of the FET. So, for which if you draw the AC equivalent, this is the circuit, this is only the FET transistor, it is being replaced by its AC equivalent model, and these two resistances are externally connected in the circuit, RG and RS. RG is from gate to the ground terminal and RS is from the source to the ground terminal. And what about this drain terminal? It has to be grounded, because we know that for AC analysis the supply and the capacitors all are short circuited and the supply is given to ground. So, the drain is connected to ground, RG is from gate to ground, RS is from source to ground, and these are the two internal parameters of FET, GMVGS and RD. So, the circuit is redrawn because these internal parameters are connected from source to ground, and this RS is also connected from source to ground. So, everything at the output side, if you see, all are connected from source to ground. So, take this as one point source from which the internal resistance, the external resistance RS and the current source, everything is connected to the ground. So, now you have to calculate what is the input impedance, output impedance and voltage gain. Input impedance, you can straight away see the circuit and tell Zi is only the resistance Rg, and output impedance Z0. What you have to do is, for calculating the Z0, you have to make this input voltage 0, and so the voltage drop across this resistance is also 0, and assume that the resistance is not connected here, because there is no voltage drop across this resistance. So, Vi is 0, gate terminal is connected directly to ground. So, the VGS and V out, that is VO, are across the same parallel network, results in VO is equal to minus VGS. If you connect this gate to ground, because there is no voltage drop here, it is connected directly to ground. So, then you will get this circuit. So, gate is now, it is grounded. So, you can imagine this is the gate, it is grounded here, and if you see the output voltage and the input voltage, that is VGS, it is just the reverse of VGS is the output voltage. VO is equal to minus VGS. See the polarity, it is plus and this is minus, and when you look at this VGS, it is minus, it is plus, it is away from the positive polarity and towards the negative polarity. This current source is away from positive and towards the negative, and from this circuit you can say VO equal to minus VGS, and this highlighted portion is the it tells you that the source terminal is common here. This is also the source terminal, all are in same node, same point. So, now apply Kirchhoff's current law at node S to calculate the output impedance. At this point, if you apply KCL, what is the equation? It is IO plus GM VGS is equal to IRD plus IRS. Okay, these two currents are flowing towards the node and these two currents are flowing away from the node. When you look at this GM VGS is towards the node, I naught is also towards the node, I naught is also towards the node, and here IRD and this the current through the resistance RS is away from the node, and so it is written here. So, replace this IRD and IRS in terms of voltage and resistance. IRD will become VO by RD, because the potential at this point is VO, that is the output voltage. So, VO by RD will give you IRD, and the voltage at this point we know that it is VO. So, VO by RS will give you the current through the resistance RS. So, it is given us in terms of voltage and the resistance here, and now IO equal to, you take this VO out. So, you will have this equation and bring this term to the right hand side. So, you will have a negative term, negative sign, and rearrange this, you will have an equation IO equal to VO of 1 by RD plus 1 by RS plus GM, and from this you can easily get the output impedance VO by IO. It is given as 1 by the resistance part, and this is the format of the 3 resistances connected in parallel circuit, and so the output impedance can be given as the parallel combination of the resistance, internal resistance RD and source resistance RS and the transconductance 1 by GM. And if you imagine, if you consider the internal resistance is greater than or equal to 10 times of RS, then you can neglect this RD part in this output impedance, and so the equation will become RS parallel 1 by GM. This is the output impedance of the circuit in with the effect of RD in the common drain circuit. This is common drain circuit. The voltage gain, the output voltage VO is determined by VO equal to GM VGS into RD parallel RS. This is the output voltage. Apply KVL around the circuit, that is the perimeter of the network will give you, if you apply KVL here, it is VI is equal to VGS plus VO, and in this equation VGS can be written as VI minus VO, and VO equal to GM into VI minus VO into, so this equation is from here GM. For this VGS, you replace this VI minus VO for this VGS and RD parallel RS, and again you multiply everything inside, and you will have an equation in terms of VI and VO. So, you know what is the voltage gain V out, that is VO by VI. From this you can get like GM into RD parallel RS by 1 plus GM into RD parallel RS. So, again if the resistance RD is greater than 10 times of RS, RD part is neglected here. So, since the denominator will have 1 plus GM RS, that is the same part as in numerator, the voltage gain the gain can never be equal to or greater than 1, because you have a 1 plus GMRS in the denominator part, and the voltage gain is a positive quantity. VO and VI are in phase for the JFET source follower circuit. So, the source follower is nothing but the common gate configuration. Why it is source follower? It is going to follow the output is following the input. And next is the common gate configuration. In the common gate configuration, the gate terminal is common to both the input and output terminals. The input is given to the source terminal and output is taken across the drain terminal, and we know that these are the resistances used for biasing the FET transistor, and Zi is calculated here and Z2 is calculated at this end. And what you have to do is you have to replace this FET in the AC equivalent model. So, if you replace it, so this is the AC equivalent circuit. If you replace the FET with its internal parameters, since the current source has to be drawn from drain to source, you will have the equation, you will have a circuit like this. So, from drain to source, we know the gate is a common terminal and so it is grounded, and there is no connection between the input part and the output part in this circuit, since the gate terminal is grounded here, and the input is given to the source, output is taken across the drain. RS is from the source to ground and RD from the drain terminal to the ground. Okay. So, now we have to calculate the input impedance. You have to redraw the circuit. The resistor RS is directly across the terminals, defining Zi. So, let us therefore find the impedance Zi which will be in parallel with RS when Zi is defined. So, the network is redrawn. Here the voltage Vi is equal to VGS, and apply KVL around the output perimeter of the network. When you look at this circuit and this circuit, when you compare, only this part is redrawn there. Since this RS terminal is connected from source to the common terminal, that is RS is connected to source to common terminal, and there is no connection between the input and output part, we have to calculate the impedance at this side, that is we have to calculate Zi dash, and this will become parallel to the resistance RS, and that is the final effective input impedance of the entire circuit. So, for which you have to redraw the circuit. Only this part has been redrawn because this Zi dash has to be calculated. So, RS need not to be redrawn here. So, after RS only this part is redrawn for calculating the input impedance. So, here this Vi is equal to minus VGS. When you redraw the circuit, it is the only part we have to be included in the circuit, the current source and the internal resistance RD. Okay, the current source and the internal resistance only has to be considered, source terminal and the drain terminal. Towards the source, the current source is pointed. So, here this is the source terminal, this is the drain terminal. A becomes the source terminal, and here this is the drain terminal. And what is V dash? V dash is the voltage at this node A. So, here when you apply KVL to the perimeter of this network, what is KVL? It is the voltage, applied voltage minus the voltage drop across all the resistances. So, V dash is the voltage at this point. So, V dash minus this voltage, minus the voltage across the resistance RD, minus the voltage across the resistance capital RD. This is the internal resistance RD. So, this is the equation comes from KVL, V dash minus VRD minus VRD equal to 0, from which the voltage across the internal resistance RD is being calculated as V dash minus this voltage VRD will become I dash into RD. It is given as I dash into RD. Just you replace this term in its current and the resistance part, it is the current flowing through this resistance is I dash. So, VRD can be replaced by I dash into RD. So, it is replaced here. So, we have just calculated the voltage across the internal resistance RD in this circuit, and now apply KCL at node A. This is node A, we know that what is KCL, the current flowing towards this node A is I dash and GMVGS. So, I dash plus GMVGS is equal to, this is the current away from the node, I dash plus GMVGS is equal to IRD, and we have calculated IRD previously. So, replace this IRD in this equation. So, I dash is equal to IRD minus GMVGS, IRD is replaced from here, it is VRD is given as V dash minus I dash RD. What is IRD then? Divided by RD will become IRD. So, this is IRD, replace this and replace and multiply and take common terms out, you will get V dash by I dash. From this equation you will get V dash by I dash, and this is nothing but Zi dash, and Zi dash is calculated as small RD plus capital RD by 1 plus GM RD. And what is Zi? It is the parallel combination of RS parallel, RS and Zi dash. Okay, Zi dash, if you replace the calculated term, it will be RD plus RD by 1 plus GM RD. So, if this internal resistance is again greater than or equal to 10 times of RD, then the equation will become, the Zi dash equation will become only 1 by GM. The previous term which we have calculated, which will become 1 by GM, because this is neglected, if RD is very high. If RD is very high, then this fraction is neglected, and 1 by RD is also neglected, and finally you will get only 1 by GM. And if you substitute in this input impedance, it is RS parallel 1 by GM. Okay, then we have to calculate the output impedance. How will you calculate it? The input terminals is the input voltage is considered to be 0, and so the effect of RS is shorted out, and set VGS is equal to 0, because Vi is equal to VGS in previous case. So, VGS now is becomes 0, the result is GM VGS is also 0, RD will be in parallel with capital RD. So, when you look at the circuit, if this Vi is equal to 0, this RS will become 0, it is shorted, and also this VGS is 0. If this VGS 0, then this part is also 0, this current is also 0, and what is the remaining resistances present? This RD and this RD. So, only these two resistances are present in the circuit, and so the output impedance will become the parallel combination of the external resistance RD and the internal resistance RD. And if again the internal resistance is greater than or equal to 10 times of RD, it is just the output impedance is just the external resistance RD. And next is the voltage gain. Apply KCL at node B. So, in this circuit, if you apply KCL, GM VGS RD is the current away from the node, and I naught or ID is the current flowing towards the node. Okay, since we have calculated, we have got the relationship between I naught and ID, it has only been taken as ID. So, IRD plus ID plus GM VGS is equal to 0. So, all the currents are flowing towards the node. So, everything becomes in the same side, that is left hand side. There is no current away from the node. So, it has become 0, it becomes 0, and from which ID is being calculated, and we have already calculated what is IRD, and we know the relation between VGS and Vi, it is just the reverse. So, replace these terms and calculate again what is ID, and from which V naught equal to IDRD, we know that, replace this ID here in V naught equation rearrange this, multiply the terms and take out the common terms, you will get the relation V out, that is V naught is equal to V I. So, V I, okay. So, V naught equal to V I, if you got the relation, then the voltage gain will become V naught by V I, V naught by V I. So, it is G M R D plus R D by R D by 1 plus G M R D, and if it is greater, then these two fraction parts will become neglected, will be neglected, and the voltage gain is simply G M R D. There is no phase shift between the input and output, it is a positive quantity, the voltage gain is a positive quantity here. And we have calculated the input impedance, output impedance and the voltage gain for the common gate configuration. And now we are going to see the DC load line of a transistor and the location of the Q point for the field effect transistor. So, here how will you draw the DC load line? DC load line will be drawn in the transfer characteristics of the field effect transistor. So, this is the voltage divider bias given to the FET. So, these are the two voltage dividers R1 and R2 going to bias the FET, and so this has become voltage divider bias, and the capacitor C1 blocks the DC voltage from its preceding circuit, and so the bias condition will not change, and this capacitance Cs is going to bypass the effect of the resistance Rs in the AC conditions. Okay. So, now for the output characteristics curve, you have to get an equation by applying a KVL at its output part, output network. So, what is the KVL equation when you apply it for the output network? It is the voltage supply minus the voltage drop across the resistances equal to 0, that is the Kirchhoff's voltage law. So, VDD minus IDRD, this is the voltage drop, VDD minus IDRD minus VDS. What is this VDS? It is the voltage difference or the potential difference present across the terminals drain and source. Okay. So, VDD minus IDRD minus VDS minus the voltage drop across this resistance. So, what is the current flowing through this resistance? We know that the current flow is, the drain current is equal to the source current. In the previous lecture we have seen that the drain current is equal to the source current, ID equal to IS. So, the same current will flow through this resistance also. So, the voltage drop across this resistance Rs is again ID Rs, that is equal to 0 finally. So, VDD equal to ID RD plus VDS plus ID Rs. This ID will be, you can take it as a common parameter. So, VDD minus ID into RD plus Rs minus VDS is equal to 0. So, you have plotted the characteristics. This is the output characteristics of JFET in its potential divider biasing. The x axis has the voltage drain source voltage and y axis has the drain current in milliamps, and these are all the curves for the constant VGS values. So, this is the VGS 0, and after which if you reduce the VGS, how the characteristics is reduced. Here you can see that. And how will you draw the DC load line? From the equation which we have derived, VDD minus ID into RD plus RS minus VDS is equal to 0. So, whenever you want to have a point at the x axis, then keep y axis equal to 0, y axis point, that is ID equal to 0. If ID equal to 0 in this equation, you will have VDD equal to VDS. So, this is one point, point B at x axis, and if you want a point at y axis, keep the x axis parameter 0. So, what is x axis? It is VDS. VDS is the value plotted along the x axis. So, if VDS is equal to 0, then VDD equal to ID into RD plus RS. We want to have a value for ID. So, ID equal to VDD by RD plus RS, that is the point. ID equal to VDD by RD plus RS, that is another point on A on the y axis. So, connect these 2 points A and B. This is the DC load line now. This is the DC load line, and for we know that for a class A amplifier, it will have it works for the whole 360-degree for its input cycle. So, you have to locate the middle of the DC load line. So, locate it at this middle point. So, it is now the Q point of the FET for class A operation. So, if you consider the middle point in the active region of FET, then it is the class A configuration. So, for which if you select this, then only the output will have all 360-degree output for full wave input in its class A class A amplifier. So, we know that how will be the location of the Q point for the remaining amplifiers. Accordingly, we can select the Q point at its DC load line in the output characteristics of transistor. We will summarize what we have seen today. The small signal analysis of FET, in which the common source configuration, the voltage gain has been derived, and common drain and common gate configuration, the input impedance and the output impedance and the voltage gain has been derived. We have taken an equation in the common source configuration of FET in the output characteristics, and by which we have drawn the DC load line on the output characteristics, and we have located the Q point on the DC load line according to the requirement. If it is a class A amplifier, you have to locate it in the mid of the DC load line, and similarly for all other class amplifiers. Questions: how do you draw DC load line and locate Q point? What is the voltage gain in common drain configuration? What is the input impedance in common gate configuration? What is the phase shift between input and output in common drain and common gate configuration? These are the references. Thank you.